Today we're diving into the world of particle physics, specifically how machine learning is being used to uncover new physics at the Large Hadron Collider. Imagine sifting through, mountains of data from particle collisions to find those subtle hints of particles beyond the standard model.
Yeah.
That's the challenge physicists face. And so instead of just searching for specific particles that, are predicted by theory, this deep dive is going to explore how researchers are using an unsupervised learning method.
Mm.
And it's detailed in a paper titled Adversarially-Trained Autoencoders for Robust Unsupervised New Physics Searches. So we'll uncover how this method works, its strengths, and its potential for, leading to groundbreaking discoveries.
Right. So traditionally, physicists have used supervised learning methods where algorithms are trained on simulated data of known signals from new particles and background noise from those standard model processes. But this reliance on theoretical models can introduce bias and also limit the potential for truly unexpected discoveries. So unsupervised learning offers a different approach.
Okay.
Yeah.
So instead of relying on simulated data, unsupervised learning trains algorithms solely on real background data, allowing them to flag anything that deviates from the norm. So it's like training a detective to spot anything out of the ordinary without giving them a specific suspect to look for, right? And at the heart of this unsupervised approach are autoencoders.
Right. So an autoencoder works by compressing input data into a simplified representation and then attempting to reconstruct the original.
Okay.
So think of it like creating a blueprint of a building. The autoencoder learns to capture the essential features of the building in the blueprint and then uses it to recreate the structure. So in particle physics, the autoencoder learns the complex patterns of standard model events.
Gotcha.
So if a new particle is present, it should stand out because the autoencoder will struggle to reconstruct it accurately.
But experimental uncertainties present a major hurdle. And these uncertainties arise from the inherent limitations of detectors in precisely measuring particle properties like energy and momentum.
Right.
So even if a new particle exists, its signature can be masked by these uncertainties, leading the autoencoder to misclassify events.
Yeah, so to overcome this challenge, researchers introduce adversarial training.
Okay.
And this involves a second neural network called the adversary, which acts like a detective trying to determine if an event's reconstruction was influenced by experimental uncertainties. So the autoencoder and the adversary are pitted against each other. The adversary tries to identify events affected by uncertainties, while the autoencoder strives to reconstruct events in a way that makes them indistinguishable to the adversary.
Interesting. So this adversarial training forces the autoencoder to become more sensitive to genuine anomalies, making it a more reliable tool for new physics searches.
Right. And researchers put this method to the test using simulated data that included hypothetical new particles decaying into top quarks.
Okay.
And the results were quite remarkable. A standard autoencoder achieved an AUC score, which measures the model's accuracy in distinguishing signal from background, of 0.717. The adversarially trained autoencoder achieved a score of 0.855, representing a significant improvement in its ability to identify the subtle signals of new physics amidst the noise of standard model events.
That's pretty significant. And the exciting part is that this method isn't limited to specific types of new particles. It works regardless of the new particle's properties like spin or color, which opens up the possibility of applying it to real LHC data.
Right.
Imagine a scenario where the data itself guides us to new particles and interactions. That's the potential of this technique.
We've seen how adversarial training enhances the autoencoder's ability to spot anomalies. But let's delve deeper into the challenges posed by those experimental uncertainties.
Right.
These uncertainties originate from the inherent limitations of detectors in precisely measuring particle properties.
So even if a new particle is produced in a collision, its telltale signs can be obscured by these uncertainties, making it harder for the autoencoder to differentiate it from background noise.
Exactly.
How did the researchers simulate these uncertainties in their study?
Well, they introduced a smearing procedure to the simulated data.
Okay.
This smearing mimics the imperfections in real detectors by adding a degree of randomness to the measured properties of particles, like their energy and momentum. This technique allows them to test the autoencoder's robustness against varying levels of uncertainty.
So it's like trying to recognize a friend in a blurry photograph.
Yeah.
The blur represents the uncertainty in the measurement, and the autoencoder needs to learn to see through this blur to identify the key features that distinguish your friend from other people in the photo.
Precisely. The researchers created different data sets with varying degrees of smearing.
Okay.
Some data sets had upward smearing, some had downward smearing, and some had no smearing at all.
Okay.
Importantly, the signal events representing new physics were not smeared. This setup allowed them to see how well the autoencoder could distinguish between signal and background under different uncertainty conditions.
And did the smearing affect the autoencoder's performance?
It did. The results showed that the direction of smearing significantly influenced the autoencoder's ability to separate signal from background. For instance, when the background data was smeared upwards, the autoencoder had a harder time distinguishing it from the signal.
Okay.
This highlights the importance of adversarial training in mitigating the impact of these uncertainties.
So the adversary acts like a filter, helping the autoencoder to ignore the distortions caused by smearing and focus on the true underlying patterns in the data.
That's a good analogy. The adversary forces the autoencoder to learn representations that are invariant to these experimental uncertainties.
Okay.
This leads to more reliable anomaly detection because the autoencoder becomes less susceptible to the fluctuations caused by imperfect measurements.
The researchers also explored a scenario where the training data itself contains a mixture of signal and background events. This reflects the reality of LHC data, which might already contain hints of new physics hidden within the vast amounts of background data.
They found that even with significant signal contamination in the training data, the adversarially trained autoencoder maintained its performance. This robustness is a crucial feature, as it suggests that this method can be applied to real LHC data without prior knowledge of what new physics might be lurking within.
So the autoencoder isn't just looking for a needle in a haystack, it's learning to recognize the unique properties of the needle even when it's surrounded by hay.
Yeah.
This makes it a versatile tool for exploring uncharted territories in particle physics. So we've explored how those adversarially trained autoencoders can handle experimental uncertainties and signal contamination. Now let's examine how this method stacks up against the traditional search techniques in particle physics.
Yeah. So traditional searches typically rely on theoretical models to define specific features of new particles and then develop algorithms to search for those features in the data. This approach can be effective, but it limits the search to the specific models being considered.
The beauty of the adversarial autoencoder approach is that it doesn't rely on those preconceived notions of what new physics might look like. It learns directly from the data, and it identifies deviations from the expected patterns of the standard model.
Right. So to compare the performance of the adversarially trained autoencoder with traditional methods, the researchers calculated the potential limits on the production cross-sections of new particles.
Okay.
This essentially means they determined the maximum rate at which these hypothetical particles could be produced without being detected by either method.
So the limits obtained using the adversarially trained autoencoder were comparable to those achieved by traditional search methods,
Right.
demonstrating the competitiveness of this new approach. This suggests that this method is not just a theoretical curiosity, but a practical tool for pushing the boundaries of our understanding.
And the researchers further tested the versatility of the adversarial autoencoder by applying it to several different new physics models, each with distinct properties like spin, color, and decay width. The results were consistent across all models. The autoencoder successfully identified anomalies regardless of the specific characteristics of the new physics being simulated.
So this finding has profound implications for the future of particle physics research. It means we can use this method to cast a wider net in our search for new physics without being constrained by, specific theoretical predictions. We can let the data guide us towards those unexpected discoveries.
Yeah.
It's really quite fascinating.
Yeah, this deep dive into adversarially trained autoencoders has highlighted the potential of machine learning to revolutionize our understanding of the universe at its most fundamental level. As we continue to gather more data from the Large Hadron Collider and other experiments, this technique will play an increasingly important role in uncovering the mysteries that still lie hidden within the subatomic world.
And as we've seen, this innovative approach allows us to sift through vast data sets and identify anomalies that might point to new particles or forces. By embracing the power of machine learning, we are entering a new era of discovery where the data itself leads the way. And perhaps the most exciting discoveries are not the ones we anticipate, but those that emerge from the unexpected deviations revealed by techniques like adversarially trained autoencoders.